Teacher, I know because only I'm the only one in the meeting. Do you even
Oh,
know?
you're the only one in the meeting.
Yes, it's only
Okay,
you and
okay.
me.
Okay. So tell me, go ahead.
Okay. Force is some type of action applied to a body. There are like two types of forces: one contact force and one non-contact force. And it,
Okay,
but I don't know its actual meaning. You can tell me, teacher.
loudly.
What,
Is that
teacher?
it? Yes.
Teacher, I don't know the meaning of forces. I only know there are two types of forces and other things. I don't know its definition.
Okay, what are the two types of forces? What do you think are the two
Contact
types?
forces, teacher, it's contact forces and non-contact forces. Contact forces are forces in which they are applied to a body by another body with coming contact with it. The examples are pushes and pulls, and non-contact forces, it is applied on an object without physically coming to contact with it. The examples are like weight and gravity.
Also magnetic, electrical.
Yeah.
Yes, electrical
Electrical.
attraction, repulsion also does not require contact. Magnetic does not require. Okay, so that is one type of classification of forces, contact and non-contact. Okay, force is basically, it is a push or pull, no matter what type you're talking about, it is a push or a pull that can cause a change. Okay, Sidra, that can cause a change. Now, what do we mean by that? What sort of change? What do you think? What sort of change are we talking about?
Teacher, change, you mean what forces do or the push and pulls?
Yeah, for example, if I push something, yeah, so yeah, I am changing the position of for example,
Yeah.
yeah, for example, this is something, and if I exert a force, what am I doing? I'm changing its position. So this force produced some change. The change can be in position, the change can be in appearance. For example, if I break it, the position won't change, but its shape will change. So that also requires force. Okay, if for example I squeeze it, I crumple it, if there's a can and I crumple it, so I'm applying force and I am causing change in its appearance. So that is also an example of a change, and that is also an example of a force.
Okay,
So
teacher, I got it.
okay, so force is any push or pull that can cause change in appearance, change also in velocity. Okay, velocity. For example, if a ball is rolling and I tap it, my tapping can change its direction,
Yeah,
right?
teacher.
And change in direction is change in, Sidra?
Direction of movement. Direction of movement.
Change in direction is change in velocity, right? What is
Yeah.
velocity, Sidra? Do you
The
know?
speed. It's the speed of an object.
Right. Sidra is right. The velocity is the rate of change of displacement with time. Right. Okay. So then another example of force is weight. Okay, weight. Now, what is weight?
Teacher, I
It
know.
is,
One question.
Sidra, you want to
Teacher,
participate? You want to tell, you want to share what weight is? Come on. Weight is, okay, Umar?
teacher, I know. Weight is the force of gravity due to the pull of the earth. It acts towards to the center of the earth, and it is a force that is pulling you downwards.
Right. So it's like a magnetic, it's also a
Yeah.
type of non-contact force. It is an example of non-contact force. And you can imagine a magnet at the center of the earth, which is pulling everything towards
Yeah.
itself. So
Teacher,
things,
it also varies in different places. It is less at the earth.
yeah, I'm coming to that, Umar. Okay. So
Okay.
yeah. Okay. So you know, force, the magnitude of force decreases when the distance between the object increases. And this is true for all sorts of forces, whether we're talking about electrical forces, or we're talking about magnetic forces, or we're talking about gravity. So as the distance from the center of the earth increases, the magnitude of the force decreases. Okay, so, and remember Newton's second law of motion. I'm talking about second law of motion, which talks about this equation. Force is equal to the product of mass and acceleration.
Yes. Okay,
Yeah.
teacher.
So when we are talking about weight, the acceleration is due to gravity, and therefore we give it a symbol G. Okay, but it is basically acceleration, which is due to a force called gravity. Okay, and this acceleration is 10 meters
Newton.
per second square. Yeah, it is 10 meters per second square. So this unit got wrong. This is not the unit for G. It is meters per second square. Remember, the unit for acceleration was meters per
Yes.
second square. I hope you remember the units. Okay. So when we multiply that, so we are using this equation. This is a Newton's second law of motion, but we are substituting acceleration by G, which is acceleration due to gravity. And the force that we get is actually the weight. Okay, the value of which is constant almost throughout the earth. But yes, you are right. It varies a little. Why does it vary, Umar?
Teacher, I think it varies because teacher, it
I just gave you a hint. Just right now I mentioned
oh
what
yes,
is.
teacher, I know, teacher. Maybe it is because of the surroundings at different places on the earth.
I just mentioned what was the factor that was affecting the magnitude of the force, Sidra? I just mentioned, just right now I mentioned, what was that factor that affects the magnitude of the force, be it electrical or magnetic attraction? Excuse me? Distance between the objects. Didn't I say that? Greater the distance, less the force. I mentioned that, right? Just right now I mentioned that as the distance between the objects decreases, do you know what gravity actually means? Gravity, see, whenever there are two objects close to each other, close enough to each other, can you please zoom out? Okay, whenever there are two objects in vicinity of each other, meaning close to each other, they exert an attractive pull on each other. They exert an attractive pull. So this body will be attracted towards this body, and this body will also be attracted towards this body. So they exert an attractive pull on each other. This attractive pull is called gravity. So this word gravity is not only for Earth. Gravity can be used for any body. I mean, even if I keep two markers here, they are exerting attractive pull on each other, and that is also called gravity. More the mass, more the gravitational pull. Okay, so this cannot pull as much as this can because this is bigger and therefore has more mass. So the gravitational pull will be greater. Okay, of this
okay, teacher, I got it.
Body on the other one. Okay, so if I increase the distance between them, if I take them far away from each other, again, the pull will get weaker. So as the distance increases between them, the attractive pull becomes weaker. Do you understand? So there are two factors. So there are two factors which affect the gravitational pull. One is the mass and the size of the objects, and the other is the distance between them. Remember this. So the gravitational pull depends upon two factors. One is gravity depends upon mass and the distance between them. Remember this, okay?
Okay, teacher, mass and size also.
Yeah, no, beta, not size, mass. Okay.
Okay, teacher. Okay.
Distance between two objects. Okay. Now, the thing is that the shape of the Earth is not a perfect sphere, but it's slightly, it's called, what is it called?
It's called a sphere, like a ball.
Yeah, it's called a geoid. Okay, I don't remember the, it's like, it's slightly oval. So it's slightly
Yeah.
compressed at the north and the south pole. Slightly compressed at the north and the south pole with the equator bulging out. Okay, that's the actual. It's not a perfect globe. I mean, it's not a perfect sphere. Okay, so the north and the south pole are a little compressed with a little bulging on the equator. So this is the center. Because of this bulging and because of this compressing, the north and the south poles are closer to the center compared to the equator. So if any point on the on equator is farther away, the distance is greater as compared to the point on either of the poles. Here, any point on exactly on the north pole will be closer to the center of the earth. Therefore, this distance is going to be smaller. Okay, this is going to be smaller as compared to this. Okay, therefore, the gravitational pull will be stronger here as compared to on the equator. On the equator, the gravitational pull will be slightly decreased, slightly lower. Why? Because the distance is greater from the center of the earth. Do you get me? So, but the difference is not too much. It's, like 0.00 something. So if you have really sensitive instrument to measure this gravitational pull, only then you are able to detect it. Otherwise, for normal practical purposes, we assume that the gravitational pull is constant throughout. Okay, there are minor variations. They're like 0.00 something or something. Okay, so this was an important point that I think is mentioned in your book as well. And then let's talk about inertia. Let's talk about the Newton's first law of motion.
Teacher, I know it. Mohsin.
Somebody in the group especially asked at night in the group that we don't understand Newton's first law of motion. And I don't know who that was. I don't remember.
Teacher,
but...
I know Newton's first law of motion.
Okay, go ahead.
Teacher, if a force is balanced, no resultant force, then if it is at rest, it stays at rest. If it is moving, it keeps on moving at a constant speed in a straight line.
Yes, basically in simple words, you can say that to cause a change in velocity, or to cause change, to cause a change in velocity or any state, we need force. Basically, Newton's first law of motion, in one word, if you want to summarize it in one word, he is talking about inertia. Okay, if anybody wants to summarize the Newton's first law of motion in one word, it's called inertia. What is inertia? Sundar, would you like to define inertia? Do you remember?
Inertia is the fact that an object will stay in its state until an external force is applied. It's resistance to any change.
Very good job. Yes, it is. And if anybody wants to, in simple words, in shortest possible words,
I can say it in simple words. It is we can say simply that it is a reluctance to start moving.
Yeah, in easy words, resistance to change, any sort of change, any sort of change. Okay, it is resistance to change. If you understand this, I mean, you can come up with fancy definitions, you can come up with big, elaborate, more explanation. But in simple words, Newton's first law of motion is inertia, and inertia means resistance to change. Now, that includes everything. If something is at rest, it would want to stay at rest until, so it will not budge until you apply some force. Okay. If something is rolling at speed, at some speed and in some direction, it will keep rolling until a force either stops it or taps it and changes its direction. If something stops it, of course, he is changing the magnitude. And if he taps it towards another direction, then the direction is also being changed. Yeah, maybe speed is also changed. That depends. But yes, he's also changing the direction. Okay, so any sort of change, it can be change in direction, it can be change in magnitude, or it can be an initiation of rolling, like it was at rest and you know made it move. So it was, the velocity was 0, and then you tapped it and it started moving. This is also change. And so this will also require force. So inertia is resistance to change. If something is, yeah, if something is moving, it will keep moving until something stops it. Now I wanna share a video, okay, in which they have shown examples of daily life examples of inertia. I want you to be able to see inertia.
Okay, teacher.
Okay, let me, yeah, YouTube, yeah, this one.
Teacher, I also already know some examples of inertia in daily life.
Okay, okay, we will. Okay, for example, now look at this. Now look at this. When the car bumped, can you see, Omar?
Yes, teacher, I can see your screen nicely.
Yeah, okay, good. Okay, so can you see when the car was stopped by the wall, what happened? The giraffe bent forward a little. Why did that happen?
I know, teacher, because it has so much inertia, and so when the car stops, it will tend to keep on moving through the windscreen, and they need seat belts. So unless
Right.
the seat belts cause a force to stop them, they will keep on moving, and they will
Right.
go broke
See,
through the
yeah, so you know, giraffe was moving with the car. So giraffe was moving with the car. The wall stopped the car, but the wall could not stop the giraffe. So giraffe's forward movement continued until he pulled himself back. So he applied a force. Okay, so he continued his motion until he applied a force and he pulled himself back, and that took some time. So let me replay it. Can you see? Yes. Okay, now this is another example. Okay, let me take it forward. Now look at this. Yeah, now let's replay it. Now I want to replay that. I want to replay that. This one. Now, when the bike stopped, did you see that the girl put the feet on the ground to stop herself? You know why? Because her motion was being continued. And if she had continued, she would have fallen. So she had to apply force to stop herself, because when the bike was moving, she was also moving, right? So her motion, the brake stopped the bike, not her. So she continued, and so she had to apply that force with her legs and with her feet to stop herself. Did you understand,
Okay,
Mohsin?
yes,
Yeah,
teacher,
okay.
I understand.
Okay, let's see another example. Now look at this. Now, when the girl pushes another girl, because she's at rest, so she wants to, inertia wants her to stay at rest. So can you see the lower part of her body does not go forward, only the upper one, because she's pushing the upper part of the body. The lower one follows later. That is also another example of inertia, because she's the pushing girl is only pushing the upper part of the body of the other girl. So you can see that the upper part of the body bends forward, but the legs stay.
Okay, teacher, I understand.
Now, look at this. Yeah, what happened here? Why did the coin, I'll replay this. Why did the coin fall in the glass, and why didn't it move along with the paper?
Because teacher, the coin is staying at one place. We just move the paper, and so if
Yeah,
okay.
because of inertia. Again, because of inertia, we pull the paper out, but not the coin. So the coin was at rest. It wanted to stay at rest because of inertia. And so it stayed at the same spot when we pulled the paper out, and the coin fell into the water. Now, my question is, why is it necessary to pull the paper out quickly? What happens if we pull the paper out slowly?
Teacher, if we put out the paper slowly, already the coin is on it, so it will move with it slowly. Otherwise, if we move it quickly, I think so it will slip because of its inertia.
If you pull it slowly, then there will not be enough time for it to change its velocity.
No,
Okay.
there
Yeah,
will be
because-
enough time. There will be enough time if you
No.
pull it out slowly.
Yeah, there will be. So that's why it will fall. But if you do it quickly, there will not be enough. So it will just like
Yeah.
stay.
You see, when the more the contact, the more prolonged the contact between the two objects, the greater the friction. Faizan, please turn your video off. Kindly, please turn your video off.
Teacher, usually she turns on the video in my classes in school. He sees my class better. So
Umar,
he usually turns on.
Umar, can I please request you to mute yourself and you raise your hand, and you will answer
Okay.
only when I, yeah,
But
you
teacher,
will
I don't
answer.
have the option to raise my hand.
Yeah,
I don't
please.
have
Yeah,
the option
mute
to raise my
yourself.
hand.
Okay, mute yourself. Okay, so that we can concentrate on the points. Okay. So no, let me. Yeah, I want to discuss this. So the longer the contact is between the paper and the coin, the greater the friction is, and so friction gets a chance to resist the motion of the coin, and so it moves along with the paper. The coin moves along with the paper. Remember, the less the friction, the greater what should I say? The less the friction, the less the motion of the coin, and so the coin will fall. Okay. Otherwise, if you pull it out slowly, the coin will be pulled along with the paper. Okay, because there will be prolonged contact between the coin and the paper. Okay, let's see. Now, look at this. Yeah. Now, here, when the paper was pulled out from the bottom of from under the notebook, this notebook fell. But now, watch this. When they're using a lot of books, then the books did not fall. And the person successfully pulled the paper from under the books. So why? Okay, I'll play it again, okay. Hello, can you guys hear me?
Yes, teacher, I can hear you.
Yes,
Yeah, I'm sorry, I got disconnected. Okay, so when we were using one book, then that book fell. Okay, we were here. That book fell. But when we are using a lot of books here, the paper is being pulled out from under the book. I'm not sharing my screen.
Not because you disconnected.
Oh, sorry. Okay, let me share my screen here. Can you see now? Okay. Okay, so this, when we have only one notebook, it's falling. See, this is not successful. Okay, when the paper was pulled out, the notebook also fell. But when we are using a lot of books, look at this. the books did not fall. Why did this happen? So why was this experiment successful with a lot of books, Sidra? And why wasn't it successful when we used one book?
Because it had more mass, there was more inertia.
Very good.
So it did not.
So these books have more mass and therefore greater inertia, whereas that one notebook had less mass and therefore inertia is less, because greater the mass, greater the inertia. Less the mass, less the inertia. Okay?
That's why.
Okay.
Also, it's hard for them to turn.
Right. Okay, let me see if there's any other. That's it. Okay. 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 Okay, so these were examples of inertia. Okay, so what are the factors that affect inertia? Can we recap, Faizan? Can you tell me?
Teacher, speed and weight and the size.
No, beta, not speed. Inertia is only affected by mass. That's it. No other factor. Okay, inertia is affected by mass only. Remember this. Okay, now another question.
But then why did the coin still like stay? Like the coin did not go with the paper, but the book did.
Yeah.
The coin has less mass than the book. Why did it has less friction too?
Yeah, but it has less friction too. Very good, Sundar.
So
And
does that mean friction is also a factor?
yes, friction is a factor. I mean, especially in these experiments, when you're pulling something out under another thing, then friction plays a role. So we want less friction. Less friction, you can see inertia easily. More friction, you know, it's difficult. Okay. So my question is, if what about inertia on the moon? Do you think inertia on the moon would be greater or less?
I think less because your weight decreases over there, right?
So inertia depends upon what? Right. Inertia depends upon only one factor, which is right. So does mass change on the moon?
No.
No. Mass stays the constant. Mass stays the same even on the moon. So as long as mass is constant, as long mass is the same, inertia will be the same. Right. Okay. So they have this question here in your book. I have the old book. I have the old book. So do you have this picture of Professor Macer's that looks an interesting moonstone? Do you have this picture, Umar? In your book? Do we have another physics for you? Okay,
Yes,
so
teacher, what? Yeah, teacher, yeah, I know. This is picture is in my book.
okay, so what is this picture showing? What are they discussing?
Teacher, in this picture, this guy, his name is Professor Messer. Also, he is on the moon. He has a rock. He is saying, wow, that's a very good rock. It is light because objects other than Earth in outer space, well away from the planets, they are weightless. So when you carry it, it feels weightless. But when you're kicking it, you will, so then when he's about to kick it, he hurts his feet.
Why?
Why? I
does
know
he?
why. Because teacher, it's this object is weightless, but its mass is still the same. So if this rock was brought to Earth, it would be very heavy.
Yeah,
And so
but
it will
he's
have
not bringing
larger
it.
mass.
Yeah, but he's not bringing it to the Earth. He's still on the moon.
I know.
So why?
So
So
when
why
he
does
kicks
the
it,
foot? Why does the foot get hurt? Is it Sundas? Yes. Yeah, because you know what he's trying to do is that he's trying to. This rock is at rest, so he's trying to kick it, and so he's trying to change the velocity.
but
And
he
so,
cannot.
so inertia.
Because
Okay,
it has
okay.
larger inertia.
Umar, please mute yourself. Okay, thank you very much, Umar. Okay, so because of inertia, because because you know this Professor Macer is when he's trying to kick the rock, he's changing the velocity because the rock is at rest. Inertia will be the same as Earth because the mass is the same, because inertia is dependent upon the mass. And so that's why he gets hurt. Okay, the reason why he gets hurt is because inertia is the same as in both moon and earth and wherever. Okay, because inertia depends upon mass. Okay. Okay. Then this experiment, I have this, these pages were missing. And so we have these photostat copies. I'm sorry about that. These are two cans. One is empty and the other, I think, is filled with sand or something. Now, they are asking, which is the harder to push? The empty can or the one which is filled with sand? That's common sense, right? Why?
Because it has more mass, so there's more inertia.
Yeah, so because when you are pushing, what are you doing? You are
Changing its
velocity.
speed.
Yeah, you're changing velocity, and inertia is resistance to change in velocity. See, whenever in physics, they use the word motion, motion is synonymous with velocity. Same thing, motion, velocity. Motion includes speed and direction, which is velocity. Okay, so this is change in velocity, change in motion, and therefore it will more the mass, more the inertia. Which has the larger mass? Of course, the one with the which is filled with sand. Okay, now tell me, which can will be harder to stop from moving? Which can will be harder to stop from moving?
The sand filled with sand.
Yes.
Because again, you're changing its velocity, so
Yes. So again, stopping is also a change in velocity. Stopping is also a change in velocity. So therefore, okay. Have you ever seen big trucks, big, lorries taking a turn?
or even the buses in Makkah.
Yeah, even the big coaches in Makkah and in Medina. Have you ever observed them taking a turn? How do they take turns?
That's why I've usually seen behind trucks with strippers stay away takes big turns.
Yes. So why, Javeria? If, for example, this is a turn, okay, and there's a big lorry coming, okay, for example, like this. Now, have you ever seen them take a turn? Such big trawlers take turns. What do? They move a little this way. Why? Because they want space for taking turns. They come all the way here. And then I wish I could show you a video of a big truck taking a turn. If you get time on YouTube, go ahead and watch, write down big trucks or big trawlers taking turns and observe how they are making turns. So they need a bigger round and they end up on the opposite side of the other road. The other road on which they want to take turn, they end up at its edge. They reach its edge. Therefore, if this road is two-way, that's a problem for big trawlers. Therefore, these drivers have to be really expert in taking turns. Why? Why is this so? Why is taking turns so difficult?
Because their mass is really big.
Yes, because taking a turn, what is it doing? Changing the direction. Yeah, changing the direction, and change in direction is change in velocity. And so greater the mass, greater the inertia. So it is difficult. Now, aeroplane. How difficult it is for aeroplane to come to a stop from flying. Have you ever noticed that? I think landing takes how long? Landing of an aeroplane takes, at least it takes 15 minutes. They announce that be ready for landing and, tie up your belts. And then when it descends and then, okay, how long does an aeroplane take? How long is it between when the wheels touch the ground and it comes to a stop? Yeah, anywhere between 5 to 10 minutes. So the brakes have been applied. Do you know? brakes have been applied as soon as the wheels of the aeroplane touch the runway. But it takes, anywhere around 10 minutes to come to a complete stop. Do you know why?
Yeah, because there's a change in velocity, so the mass will be big, so then there's inertia.
Right, inertia. Why is the inertia so much? Because the plane has a lot of mass. Plane has a lot of mass.
For war, they need small like jets because they don't have this inertia.
Why do aeroplanes need runways at the first place? Why do we need airports? Why can't aeroplane land, like anywhere on any road? Because it requires a space to run before it comes to a stop, and because it has a lot of inertia. Do you think if anything, God forbid, comes in front of that landing aeroplane, do you think that aeroplane can immediately change the direction or can, stop? No way, no way, no way. Aeroplanes cannot do that. If anything, God forbid, comes in front of it, it's gone. It's gone. It's really, really hard. Okay. So these are a few examples of inertia. Then, okay. Were there any more experiments here that we need to discuss? Okay, this is a picture, good picture. They're showing a crash. Again, when the brakes are applied, the car stops, but the passengers continue to move. And when they continue to move, accidents happen. Okay, so that's why seat belts are recommended. Okay, this is another example of inertia. Okay, and then I think let's move on to the spring. Okay, extension of a spring. I think we have discussed inertia enough. Okay, where did that go? Okay, what is extension? What is extension? Yes, Javeria? What is extension? Okay, so I hope you guys are with me.
Teacher, extension is directly proportional to a stretching force.
Yes, teacher.
Yeah, but my question is, what is extension?
Teacher, it is like extension.
You guys don't know?
Teacher, an increase in size.
Very good. Yes, yes. Extension is increase in size. For example, this is a spring balance. Okay. See, materials have elasticity. What does elasticity mean? What does the word elasticity mean? What is the definition?
Elasticity means that if, for example, if you put a weight on, for example, the spring, as soon as you remove the weight, it's gonna come back into
Right.
its form.
Right, very good. So elasticity is the ability of a material to regain its original shape after the force is removed. Okay, it is the ability of a material to come back in its original shape after the force is removed. So now we have this spring balance and we make use of its elasticity. We make use of this extension and its proportionality with load, as you mentioned, to measure the forces. Okay, but let's just start. For example, in order to be able to use a spring balance, we should know its original length. Original length meaning what is its own length without any force acting upon it. Without any push or pull, what is its original length? So once we know the original length of a spring, then we can put some weight, okay, a known weight, such as 10 newtons. If 10 newtons hangs on it, of course, the weight will be directed towards the center of the earth. Now, with the help of a meter ruler, we can use a graduated meter ruler. Okay, a graduated meter ruler, we can see the new length. I mean, we can measure the new length. Now, Extension would be the difference between this new length and the original length. For example, now the length is 60 centimeters. The total length on the meter ruler is showing that the new length after hanging 10 newtons is 60 centimeters. So what would be the extension?
It would be 10 centimeters.
Yeah, it would be 60 minus 50. So remember, extension is always the new length minus the original length. Always remember this. Okay. And it is the extension which is directly proportional to the force or to the load. This is called load or force. Now, if we hang 10 more newtons, and now 20 newtons are hanging from the spring balance, there is further increase in the length, and now the new length would be 70 centimeters. So now what would be the extension? At 20 newtons, what is the extension? Use this formula. New length is 70. Yeah, 70, no, not 30, 20. New length is 70 centimeters. Original length was 50. So 70 minus 50 would give us 20 centimeters. So the extension at 20 newtons is 20 centimeters. So whatever the new length you get, you subtract the original length from it and you will get the extension. Okay. Now, remember that if you are plotting, have you guys done graph plotting of this? Omar, Faizan, Javeria?
Yes, teacher. This graph plotting.
Yes. Have you done graph plotting?
Yes, teacher, we did graph plotting.
Yes,
We
teacher.
did
there
graph
is a
plotting,
photo
teacher,
proportionality.
and we can also mark the limit of proportionality.
Okay. So if you guys have done graph plotting, then I will discuss the graph. Okay. So this is, I don't know what page number it is on your book. Yeah, can you please leave it? Yes, yeah, leave it. Let me do it. Yes. Now this graph with the load or the force on the x-axis and extension in the y-axis. Remember, this is extension. This is not the length of a spring balance. Sometimes they might give you length, the actual length. If they give you actual length, then I will show you how that will differ. That will change, that will affect the shape of the graph. Okay, another thing is that if you have force on the y-axis and if you have extension on the x-axis, then again, the shape of the graph will be different. Okay, but usually they use force or the load on the x-axis and extension on the y-axis. Now, what is this shape teaching us? What is this shape of the graph telling us? What sort of relationship is there between force and extension?
As the weight increases, extension increases.
Right. And as the force is increasing, the extension is increasing by the same.
What, teacher? Teacher, I can't hear you.
Teacher, I can't hear you.
Me neither.
Me neither as well.
Yeah, okay. Now can you see, can you hear me?
Yes, teacher, we can hear you now.
Okay. Sorry about that. Okay, so what I'm trying to show you is that the y-axis is the length of a spring. It is not extension. It is the length of a spring. It is not the extension. So can you see now, look at the shape of the graph. It is still a straight line. And as the load is increasing, the length is also increasing. But can you see that the graph is not passing through zero? Graph is not passing through zero. Why? Because this y-axis is representing the actual original length of the spring. So even when you have 0 Newton, even when you have no load on the spring balance will have its original length, right? So make sure that you always plot. I mean, it depends upon the question, what the question has asked you to plot, okay? So be careful of what the question has asked you. Sometimes students get confused and they don't calculate extension and they directly plot the length of the spring against the load. And so this is what they get, okay? So if, you know, looking at this graph, if somebody asks you, okay, now what was the original length of the spring here? The original length of the spring here is 10 centimeters because at 0 newtons, the length of this spring was 10 centimeters. Okay, so this is what I was trying to mention. Okay, so when you have two quantities which give you a straight line passing through the origin, this is called the origin, then you say that they are directly proportional. When two quantities are directly proportional, and if you want to, so what can we say? We will say that force is directly proportional to extension. F for force, E for extension. What does this symbol mean? This symbol means directly proportional. Now, if we want to convert this into an equation, we will have to use some constant. Constant meaning some value that each time gets multiplied by extension to give us force. And the value of this stays the same for a particular spring balance or for a particular material. As long as the material is the same, this constant is also going to be the same. So this constant is different for different materials, for different spring balances, okay? So this is called the constant of proportionality, or in case of a spring balance, it's called a spring constant. It's called a spring constant. How do we get the unit Newton per meter? Easy. What is the unit for force? Newton. Okay. What is the unit for extension? Meter or millimeter, whatever. Yeah, meter. Okay. Let's take the basic SI unit, meter. Okay. So then this constant will have a unit of Newton per meter. You know, rearranging the equation. The unit for this constant would be Newton per meter. So this is the constant of proportionality, or the spring constant, which will vary with the spring or the material that you're using. Okay. Now, what is the elastic limit? So remember, what is Hooke's law? Hooke's law is that the extension is directly proportional to the stretching force, meaning that as the force is increasing, the extension will also increase by the same amount. If you have put 3 weights on the spring balance, and right, yeah, and then when you remove the 3 weights, the spring will get back here. It will get back to 0 extension. That means it has elasticity. Elasticity is the capability of coming back to its original shape after the forces are removed. And this will hold true for as long as you are within this straight line. So till 5 weights, the spring has the capacity to come back to its original shape as you remove the weights. But what happens if you put 6 weights? Now it will snap, or it will get permanently deformed. And if you remove the weight, the spring balance will never get back to 0. It's gone. It has been deformed. It has been deformed. So if a spring is taken beyond its limit, it will not return to its old shape. It is permanently deformed.
But what if you want to weigh more than?
So yeah, you'll have to use some balance that can withstand that much force. Okay, so that's why we have to choose the spring balances according to our needs. So if you have a big force to measure, you will have to use a stronger spring balance. Okay. Okay, so this is this point at which the graph is no longer a straight line, but it turns into a curve. This point is called the elastic limit. It is called the elastic limit. And very often they ask you to plot graphs and point the elastic limit. So how will you point? How will you mention? We will do that. You will point you will plot the points on the graph. You will join them with the help of a ruler. And because there is direct proportionality, make sure that the line passes through the origin. Okay, and as soon as you see that the graph has left the straight line, that's where the elastic limit is. So the spring will no longer get back to its original shape. So let's do a few end of chapter questions and it will be clear what we mean. I think question number one is really easy. Do you guys want me to do, are there different questions in your new book?
Teacher, your question 3 is our question 2, and question 1 is also included in question number 3.
Okay, so question number 2 and 3 are the same?
Yes, teacher, we know them. How to do? We just did not did question. We just did not did question number 1, part G and part B. We know. Otherwise, we know question number 1, 2, 3. We did it with our physics teacher.
Okay, so no need to discuss, right? They're easy, right? Sidra, what is her weight on Earth? Just multiply this by. Okay, remember, if the unit is in kilogram, only then you multiply by 10. Simply. If you get this in grams, you will have to convert it into kilograms first before multiplying by 10. So just take care of the units. Otherwise, it's just simple multiplication by 10. Okay, what is her weight on the moon? Divide the Earth's value by 6 because the gravity on moon is 1/6. Okay, what is her mass on the moon? The mass is going to stay the same, right? So let's not waste our time on this. Let's move on to question number 4. Is this question in your new book?
Yes.
Yes, teacher, this is.
Okay, a spring is 20 centimeters long when a load of 10 Newton is hanging from it, and 30 centimeters long when a load of 20 Newton is hanging from it. Draw diagrams and work out the length of the spring when there is no load on it, and then there is a load of 5 Newton on it. So I plotted that graph that I just showed you. So what did I do? My x-axis again has load in newtons, remember. Now, what are the prerequisites of plotting a graph? Always you should show your x-axis, y-axis with arrowheads on both the sides. Without this, the graph would be incomplete. Also mention the quantity which you are representing on each axis with units in brackets or units. Okay, do not forget the units. If you forget the units, your marks will be deducted even in board exams. Okay, and then you have to see length of a spring in centimeters. Okay, I have to mention the units. Okay, then also make sure, now I did not do this, but make sure that you are using at least 2/3 of the graph paper, 2/3 of the graph paper that is provided to you. Okay, also make sure that you are using an appropriate scale for both x-axis and y-axis. Okay, such as, what do I mean by scale? Such as 1 big square is equal to 5 newtons on my scale. 1 big square is 5 Newton. So what did the question say? The question say that at the load of 10 Newton, the spring is 20 centimeters long. Remember, now that means this is the length of the spring. It is not an extension. Okay, so you will not have a graph passing through the origin. So 10 Newton is here and 20 centimeters is here. Okay, that's 1 point. Then I have 20 Newton, 30 centimeters. So 20 Newton is here, 30 centimeters is here. So these are the only 2 points they gave me in the question. I will join them and then I will extend the line till the y-axis. Where it is cutting the y-axis, that is the original length of the spring balance. Are you with me, Sidra? Also, there are 2 ways of plotting the points on the graph. Either you put a cross or you put a really clear point and it should be exactly on 1 point. You know, your dot should not be as big as encompassing like something like this. If you make a dot like this will not be accepted in IGCSE. Okay, and also circle it for your ease, for your convenience, as well as the examiner's convenience. Then it's easy for the examiner to check that you have plotted the points correctly. And then with the help of a ruler, you join them this way. Okay, like this. Okay, I think you guys are plotting graphs for the first time in physics in grade 6, right? Or even in math, if you have never done it. Right.
Teacher, we did not study plotting graphs in maths. We're still on algebra.
Okay.
Teacher,
Okay.
I have
Yes.
a question.
Yes.
What is the weight on moon? What is the answer of that? How do we have to find the answer?
Oh, okay. Okay. So when there is okay, what was draw diagrams and work out the length of the spring when there is no load on it. So that we know is 10 centimeters. Then there is a load of 5 Newton on it. So I will find from the graph 5 Newton and I will see where is it meeting the line. What is the y-axis value? What is the corresponding y value? So when I counted the boxes, I know that this is cutting exactly midway between 10 centimeters and 20 centimeters, which is 15. 15 is exactly between 10 and 20, right? So that means at 5 Newton, the length of the spring would be 15 centimeters. Okay, Faizan? Okay.
Teacher,
So
I had another question in question number 3. What is her weight on the moon? How to find the weight on her moon? What is her weight on the moon? How to find that?
okay. So did you calculate the weight on the earth?
Yeah, teacher, the answer is 600.
Right. You divide that by 6.
Okay, teacher.
Why? Why are you dividing? Do you know?
Because the weight is 6 times more.
Teacher, we are dividing because the amount will get less because minus is equal to divide. And
Sorry, the weight on the moon is 6 times less.
Yeah, the weight on the gravity of on the moon is 1/6 that of the gravity of Earth. Do you understand? So if, for example, on Earth, it is 10, so the weight is 600 newtons, right? Then we will use the same formula for moon. The mass is 60 kilogram, but the gravity is 1/6 of that, right? 1/6 of that, 1/6 of this. So again, 600 multiplied by 1/6. So you will get 100 Newton. Or another way of doing this is that if you know the value of G for moon, if you know the gravity due to acceleration, acceleration due to gravity on moon, then you can put in that value. Well, that value, even if you put in that value, you will get around about the same answer because that value is 1/6 of 10. Okay, so you will get almost the same answer. Okay, did you understand? Was that Faizan? Okay,
teacher,
Teacher, I have a question that what mass on the moon? I couldn't understand how to calculate the mass on the moon.
Beta, mass will be the same as on Earth. There's nothing happening to the mass. Mass is the same. Okay, what is the difference between weight and mass?
teacher, the weight changes on the moon or other planets or the stars, but the mass stays the same.
See, weight is a pull. Weight is a pull. Okay. Mass is
gravity.
yes. Like, for example, let me give you an example if you're getting confused. For example, this is an object and it has, for example, let's suppose these are atoms making this, okay? This is another object and it has a lot of atoms, lots and lots. I don't even have time to make all of the atoms, but you get the point, right? Now, each particle is getting pulled by gravity. Each atom is getting pulled by gravity. Now, if I add all these pulls, what I get is its weight. If I add all of these pulls, what I get is weight. Now, all these atoms are also getting pulled. Okay, so like there are lots and lots of them. Okay, I don't have time to make all the arrows. So if I add all these pulls, again, this is the weight of this bigger object. So let's say this is a small object, this is big object. So which one do you think it will be greater? This will be greater, right? Because it had more atoms being pulled. So there are more pulling forces acting upon this, right? So weight of the bigger object will be greater than the weight of the smaller object, right? Right. Now,
Yes, teacher.
yes. So the weight will depend upon, and also it will depend upon how strong they are being pulled. So in the moon, they are being pulled weakly. Weakly meaning the pull is weak. On the earth, the pull is stronger compared to moon. So therefore, see, weight will depend upon the gravitational pull. It is the gravitational pull that changes when you go from earth to moon. The mass is the number of atoms. That stays the same. If I go to the moon, my whatever number of atoms are in my body, they will stay the same. I did not lose any atoms here, did I? No. But yes, the gravitational pull, which is pulling me towards the moon, towards the center of the moon, will be weaker. Did you understand?
Yes, teacher.
So mass will stay the same on the moon. The mass will be 60 kilograms. Okay, is there any confusion in question 1 and 2? An object has a mass of 4 kilograms. What is its weight in newtons here on Earth?
Teacher, but you did not understand my question. But I was asking that how to calculate mass. Calculate the mass.
Yeah, when we come across a question like that, then you will understand. I mean, mass can be calculated by this equation as well. It will depend upon what information is given in the question. So if you know the value of G, and if you know the value, the weight, you can calculate mass. Okay.
Okay, ma'am.
So how will you calculate? For example, the weight is 10 Newton. Okay. For example, the weight is 10 Newton, and the question is asking you to find out the mass and on Earth. And on Earth, the value of G is 10. So now it's easy, right? Mass will be, the mass will be 10 divided by 10, which is 1 kilogram. Okay.
Yes.
And remember, we use the units kilogram with when we multiply it by G. Okay.
Yes.
We cannot multiply mass in grams with G. You will have to convert it into kilograms before you multiply by 10. Okay.
Yes.
Okay. Okay. So, okay, let's move on to this question. Question number 5. Do you have this question in your new book? Okay. In a spring experiment.
Yeah.
Okay. Okay. I'm getting late. It's beyond 7 o'clock, but okay, let me just really quick discuss these questions and then we'll end the class. Now, in a spring experiment, the results were this. So they have given us this table. We have load in newtons, we have length of the spring balance here, and then we have extension. Now, what is the length of the spring when unstretched? It's so easy. Come on, tell me. What is the length of the spring when it is unstretched? Who will answer this question? Yes, Javeria?
50.
Right. How do you know? How did you figure that out?
Well, because in the table it shows that there's zero load, so it means that there's no
Right.
extension, and so
Right.
it should be 50 millimeter.
Right, right. So I hope everybody understands that. Everybody is clear on that. When there is no load, the actual length is what you're going to have. I mean, as you're reading, right? Now copy and complete the table. So now they want you to write the extension for each load. And how do you calculate this?
You subtract the length of the load.
Right, I told you this formula. Extension is new length minus the original length. So what you do is new length minus the original length. Original length in this case is 50 millimeters, and take care of the units. Your units should be in millimeters. Okay, so 58 minus 50 is 8. 70 minus 50 is 20. 74 minus 50 is 24. 82 minus 50 is 32. 90 minus 50, and so on and so forth. So you subtract the original length from all these lengths, and then you write down your difference here. That will be the extension. Did you guys understand that?
Yes, teacher.
Yes.
Teacher, I was asking that how we got the answer of 50, the first zero load.
This, yeah, here extension is 0 because it is exactly on at its original length. It is exactly at its original length, so extension is 0. No, there's no extension. Okay.
Yes. Okay. Thank you.
Okay. Is there? But did you understand the other values? Okay. So once you
Yes,
have completed, okay, once you have completed the table, then you just have to plot a graph of extension against load. Now, if they said length against load, then you would be using these values, length. Okay, but they asked you to plot a graph of extension against load. So now I have plotted this. This is question number 5, right? Okay, so again, be careful. Can you zoom out? Yeah. Okay, so your x-axis should have arrowheads, your y-axis should have arrowheads. Okay, you're on x-axis, you have load in Newton. On the y-axis, you have extension in millimeters. Okay, and did you see that when we had extension, the graph is passing through the origin? Okay, so what did I do? Load 0, extension was 0. Load 1, extension is 8. Now zoom in. Sorry. Zoom in. Okay. Okay, so when load is 1 Newton, so follow the table. Okay, follow the table with me. I hope the table is right in front of you. So keep that table in front of you and then follow me. So 1 Newton, it's 8. Okay, with 2 Newtons, it is 20. Okay, with 2, it is 20. With 3, it's 24. Okay, with 4, it's 32 here. Okay, and so on and so forth. Okay, I hope you guys know how to plot a graph. If not, practice, practice, practice. With practice, you will learn. Okay, now what is the other part? One of the results is wrong. Which is it? What do you think it should be? You know what I did? So I had all these points and I saw, and I tried to join them with the origin, because the graph has to pass through the origin. Okay, no matter what the situation is, the graph has to pass through the origin. And so I tried this. When I tried this, I saw only 1 point. My ruler is touching only 1 point. But when I kept my ruler this way, I could join up like 4 points. Okay, 4 points. And there are a total of 4, 5, 6, 7. So out of 7, I could join 4 points in one line. So this is the best fit. So I chose this. Okay. Also, I noticed that these last 2 points are not coming on my straight line. So maybe the spring balance lost its elasticity. And so maybe this is the elastic limit, right? And so that's how I got this graph. So I joined all of them, and then with my hand, I joined these points. Okay, so now I have curves. So I have a straight line till here. I have a straight line till here, then it's a curve. Okay, so this is the elastic limit. Okay, it is still here that the balance is following Hooke's law. The balance is following Hooke's law only till 5 Newton. Okay, now let's see. So one of the results is wrong. Which is it? This point is the only one which is out of my graph. So this is the wrong one. This result is wrong. So how will I write? I will say that the result, the 2 Newton with 20. This one is wrong. 2 Newton with 20 extension. This one is wrong. Why? Because it is not falling on my graph. That's why. What do you think it should be? Then I will see what value am I getting on the graph. On to what am I getting? This is 16. This is 16. Zoom in. I always do this. Can you see? Wait, let me.
Yes, teacher, we can see.
Yeah. Yeah, you can see. So it should be 16 millimeters. It should be 16 millimeters. Okay. Then the next part is mark the elastic limit on your graph. So the elastic limit, how do you figure out the elastic limit? Keep a ruler and look at where the graph is leaving your ruler. Okay, I kept the ruler and make sure the ruler is passing through the origin, and see where is the graph leaving your ruler. It's leaving it here. This is the last point. It is the last point on the line which is on the ruler. Okay, then the line is deviating away from the ruler. So this is going to be my elastic limit, the last point. Okay, what load gives an extension of 30 millimeters? Extension of 30 millimeters. Okay, so 30 is here. I draw a line. I find out what is the corresponding value on the x-axis. And when I count, it is 3.75 newtons. 3 is here, 4 is here. Exactly in between, we have 3.5. Okay, and then I count these boxes, 3.6, 3.7, and then exactly between 3.7 and 3.8 is 3.75. So that is my answer. Can you see me? Can you understand how I am working this out? Can you understand how I'm working this out?
Yes.
Okay. Have you guys done this question with your teachers, school teachers?
No, teacher, because in the assessment, only question number 1 and 2 are included.
Oh, this is not included? I asked you and you said yes.
No, this is not included.
Okay, what would be the spring length for a load of 4.5 newtons? So I find out 4.5 newtons and I trace back on the graph, and then I look for the corresponding value on the y-axis, and it is 36 millimeters. 36 millimeters. Okay, so spring, what would be the spring length? Okay, pay attention. They are asking the spring length, not the extension. This is an extension. Remember, this was extension. So how can I get the original length from extension? Can anybody tell me? They are asking what would be the spring length for a load of 4.5 newtons. What would be the spring length? So this is extension. Javeria?
We shall add the extension into the original length.
Very good. Good job. Yes. So you add the extension to original length, you will get the spring length. Okay. Let's move on. This picture, I think we have discussed this already. Should Professor Macer pull the tablecloth quickly or slowly? Explain the physics of this trick using the correct scientific words. So Professor Macer is pulling the tablecloth and the dishes must be staying on the table. So what's going on? Who is gonna explain this? Sidra?
So the dishes are gonna stay because of inertia.
Very
He's
good.
gonna pull it quickly, and so the dishes will stay, but the cloth will.
Yeah, quickly, because you know, if it is pulled slowly, the dishes will have prolonged contact with the table and with the tablecloth, and the cloth will be able to pull them. Right? So that's
If
why.
we pull it slowly, the dishes will fall, and if we fast,
We
then it
cannot
will.
hear.
Oh, okay. So she just said that it is due to inertia and that the dishes will stay on the cloth because, you know, he pulled the tablecloths really quick, did not give them a chance to be pulled along with the cloth. And so this exhibits inertia. Okay. Now, question number 7. An engineer needs to know how far a long steel beam will sag under a load. The table shows some results. So again, we have a similar table. Okay, sag will be taken as extension. Plot a graph of the sag H against load. One of the measurements of H is wrong. Which is it? What do you think it should be? So it is a similar question. It is a similar question. Okay, again, same graph of load against, now I will call it sag in centimeters. The unit will be centimeters. Okay, zoom out so that they can see. Yeah, this is how my whole graph looks like. Okay, and so I plotted all the points. I'm not going to go into the details of the of each and every point because we are running short of time. Okay, you get the point. And so which one is wrong? Which value is wrong? Oh, yeah, this one. This one. Can you see all the points are falling exactly on the line neatly, except for this one, this one is not, okay? And do you think it is bypassing its elastic limit? Yes, just bypassing a little here. Here is the elastic limit, okay? Now, what do you think it should be? What do you think the actual value should have been? So you go down 1, you have to be on the graph, on the line. So this is, what value was this?
Ma'am, it should be 6.5.
Yes, it should be 6.5. I don't remember exactly. It did not, I forgot to mention it here. Yeah, it is 6.5. Okay. 6.1, 2, 3, 4, 5. Yes, 6.5. Yes, it's 6.5. Okay. What is the sag for a load of 4,500 Newton? So you plot against 4,500 Newton, look for the corresponding value, and it is 9. 9 centimeter is the sag. Okay. Then next part, what load would give a sag of 52 millimeters? Now they tried to trick you. They gave sag in centimeters, and then they're asking you to calculate the load for some sag in millimeters. So you will convert this centimeters, you will convert this millimeters into centimeters. This is 52 millimeters. So what will this be in centimeters, Sidra? 52 millimeters will be what in centimeters? Just divide by 10. There are 10 millimeters. 5.2, right? So 5.2. 5.2, and what is the corresponding load? It is 2,600 Newton. Okay, 2,600 Newton will be the answer. Okay, would a longer beam sag more or less in a sketch its
Miss, I
graph
don't
on?
understand.
Beta, I just plotted a graph. It is similar to the last question we did. Okay, I am not explaining in too much detail because I've already explained one graph and then we are running out of time. So what did you not understand? Can you please ask me exactly? I am following all these parts one by one. Sometimes they are asking what will be the sag against a load of this. So I have to find out the load on the x-axis, and then I have to trace it to the graph and then look for the corresponding value. That will be my answer. Corresponding value on the y-axis that will give me sag, because sag is my y-axis. You understand sag? Sagging is this, you know, this beam sagging downwards due to this load acting upon it. Okay. So would a longer beam sag more or less? Yes, Sidra?
It would sag more
Why?
because the length would be longer. So
Yes, I think so too. A longer beam will sag more because there will be more length without support, and so it will have more space to sag. Now sketch its graph on the same axis. Now, so this graph was for this beam. Now, if you have a longer beam, how will the graph differ? How will the graph differ if you have a longer beam? Yes, Sidra?
Then what does this means longer beam?
Longer beam, B-E-A-M.
Then what does this mean?
Beta, rod, a rod, simple.
Oh,
Rod or slab or whatever. Yes.
okay.
Okay, so how do you think the graph will be different if we have a longer beam? Extension will be, oh sorry, sagging will be more, right? So for each corresponding load, you will have greater sagging. For each corresponding load, you will have a greater sagging, right? So, I mean, I cannot exactly plot points because they did not give me values, but roughly, I will make a graph this way. I will make a graph this way. You know why? First, yes, okay. So yeah, go ahead and elasticity. Yeah, okay, something like this. So what roughly what you're trying to say that for each corresponding load, you had a higher sag, and also but the direct proportionality Hooke's law still exists, and that is why the graph is still passing through the origin. Okay, but for each corresponding value of the load, you have greater sag. Okay, so you will have a higher, steeper graph, a steeper line on the graph. Okay, did you guys understand this last part?
Yes.
Yes.
Okay, question number 8. Okay, let's focus on this. Second last question. Could he lift the ball more easily in a prison on the moon? Could he jump higher in a prison on the moon? Could the convict escape this way? Now, if you look at the picture, what is the convict doing? He has a steel ball, which is chained to his foot, and he is trying to throw that ball, right? So what will happen when he throws the ball?
The ball is heavy and he's tied with a chain, so the ball will fall on him. It won't go over the wall.
Yeah, I mean, the ball will fly as he throws it, but then the ball will pull on the chain, will also pull his foot and leg, but because his weight is greater than the ball, his weight will eventually pull the ball back.
why can't he?
So he'll fall.
Why can't he simply untie himself from his foot with both hands?
Okay, could he lift the ball more easily in a prison on the moon?
Yes.
Okay, why?
Because
Explain.
there will be because there
Then
is
because
no
there is less gravitational.
there's no
Very good.
gravitational pull, so the weight will
Yes. Yes, because the gravity is less and so the weight is less and so he can easily. Okay, could he jump higher in a prison on the moon?
Yes, ma'am. Yes, ma'am.
Again, due to?
Because gravitational pull.
Yes, yes, very good. Okay. Now we haven't done, you guys haven't done circular motion, right?
Yes, we have not. Yes, ma'am.
No. Okay, so this last question is regarding circular motion. So is there any question that is in your book and that I haven't discussed you want to ask? Is there any confusion that you want to ask?
No, ma'am. No, ma'am.
Okay, then good. Best of luck for your exam and for your tests. Okay? Okay, assalamu alaikum wa rahmatullahi wa barakatuh.
Okay, happy, ma'am.
Allah Hafiz.
Hafiz.